To this point, I've developed a methodology for measuring single events, which was useful for troubleshooting the methodology. For it to be more useful, it would be good to annualize the greenhouse gas emissions resulting from hazards, so that they could then be included in a climate action plan, or used to measure the impact of hazard mitigation policies on greenhouse gas reduction. The annualization process is straightforward and relies on two important graphs. The first is the probability of occurrence of a certain hazard. On a log scale, they typically look like this regardless of the hazard. There's a high likelihood chance of small events and a low likelihood chance of large events. The other graph is the fragility curve. Fragility curves are used to describe the probability of a certain damage state given a certain hazard level. For a residential home, this is what a minor damage fragility curve might look like. These two graphs are combined to determine the annualized probability of failure. Here I show one iteration of the process where magnitude 7 values for each are chosen. Needless to say, there's a lot that goes into these graphs. Luckily for me and for California jurisdictions, the California Geologic Society does all the heavy lifting, using a combination of their own earthquake data and HAZUS to develop an annualized building structure loss by census district. This data can be used a lot of different ways, but it's the perfect data set to match the LCA methodology to determine the annualized greenhouse gases associated with earthquake damage. For the purposes of this thesis, I chose 4 specific jurisdictions in the Bay Area to complete an annualized assessment of. The cities of San Francisco, Alameda, Oakland, and Berkeley were all chosen because each has a climate action plan. Each was recently chosen by the Rockefeller Foundation to receive $1 million to be spent on resilient planning, and lastly because the San Francisco Metropolitan Study Area, which includes all of these cities, has the second greatest earthquake risk in the state of California. Using the CGS dataset, I could combine the census districts of each city to understand the annualized building earthquake loss in either percent of structure lost or in total dollar losses. Using the EIO process, the annualized loss data is converted into GHG emissions, and can then be compared to the overall GHG emission inventories produced by each city's climate action plan. Using this data and the EIO method, the annualized GHG of building losses due to earthquakes is about 1% of each jurisdiction's climate action plan. So, not the most dramatic results, but let's revisit what I've just said. 1% is only considering building losses, not building contents and not infrastructure and vehicles. Second, this only considers earthquakes, including fires, floods, and other hazards may increase this further. Conversely, this is 1% of existing CAP inventories, which do not measure embodied emissions of the products consumed by cities. If climate action plans begin to measure emissions beyond just transportation and building energy use, the 1% share of earthquakes is likely to shrink. Weighing all these factors, earthquakes represent roughly 1% of the region's current greenhouse gas emissions. Knowing what the baseline is, the region or individual cities can adopt hazard mitigation policies that have the added bonus of being measurable greenhouse gas reducing strategies.